In mathematics, two quantities are in the golden ratio if their ratio is the same as the ratio of their sum to the larger of the two quantities. The figure on the right illustrates the geometric relationship, expressed algebraically, for quantities A and B with A greater than B greater than 0, where the Greek letter phi represents the golden ratio. Its value is A001622. The golden ratio also is called the golden mean or golden section. Other names include extreme and mean ratio, medial section, divine proportion, divine section, golden proportion, golden cut, and golden number. Some 20th century artists and architects, including Le Corbusier and Dali, have proportioned their works to approximate the golden ratio, especially in the form of the golden rectangle, in which the ratio of the longer side to the shorter is the golden ratio, believing this proportion to be aesthetically pleasing. The golden ratio appears in some patterns in nature, including the spiral arrangement of leaves in other plant parts. Mathematicians since Euclid have studied the properties of the golden ratio, including its appearance in the dimensions of a regular pentagon and in a golden rectangle, which may be cut into a square and a smaller rectangle with the same aspect ratio. The golden ratio has also been used to analyze the proportions of natural objects as well as man-made systems such as financial markets, in some cases based on dubious fits to data calculation. Two quantities A and B are said to be in the golden ratio phi if one method for finding the value of phi is to start with the left fraction. Through simplifying the fraction and substituting in B, A equals 1, phi, therefore, multiplying by phi gives, which can be rearranged to using the quadratic formula. Two solutions are obtained. And because phi is the ratio between positive quantities, phi is necessarily positive. History. The golden ratio has been claimed to have held a special fascination for at least 2,400 years, though without reliable evidence. According to Mario Livia, some of the greatest mathematical minds of all ages, from Pythagoras and Euclid in ancient Greece, through the medieval Italian mathematician Leonardo of Pisa and the Renaissance astronomer Johannes Kepler, to present-day scientific figures such as Oxford physicist Roger Penrose, have spent endless hours over this simple ratio and its properties. But the fascination with the golden ratio is not confined just to mathematicians. Biologists, artists, musicians, historians, architects, psychologists, and even mystics have pondered and debated the basis of its ubiquity and appeal. In fact, it is probably fair to say that the golden ratio has inspired thinkers of all disciplines like no other number in the history of mathematics. Ancient Greek mathematicians first studied what we now call the golden ratio because of its frequent appearance in geometry. The division of a line in two, extreme and mean ratio, is important in the geometry of regular pentagrams and pentagons. Euclid's Elements provides the first known written definition of what is now called the golden ratio. A straight line is said to have been cut in extreme and mean ratio when, as the whole line is to the greater segment, so is the greater to the lesser. Euclid explains a construction for cutting a line in extreme and mean ratio, i.e., the golden ratio. Throughout the Elements, several propositions and the proofs employ the golden ratio. The golden ratio is explored in Luca Pacioli's book De Divina Proportione of 1509. The first known approximation of the golden ratio by a decimal fraction, stated as about 0.6180340, was written in 1597 by Michael Maestlin of the University of Tübingen in a letter to his former student Johannes Kepler. Since the 20th century, the golden ratio has been represented by the Greek letter phi, or less commonly by tau. Timeline according to Priya Hemingway. Phidias made the Parthenon statues that seem to embody the golden ratio. Plato, in his Timaeus, describes 5 possible regular solids, some of which are related to the golden ratio. Euclid, in his Elements, gave the first recorded definition of the golden ratio, which he called, as translated into English, extreme and mean ratio. Fibonacci mentioned the numerical series now named after him in his Liber ABC, the ratio of sequential elements of the Fibonacci sequence approaches the golden ratio asymptotically. Luca Pacioli defines the golden ratio as the divine proportion in his Divina Proportiona. Michael Maestlin publishes the first known approximation of the golden ratio as a decimal fraction. Johannes Kepler proves that the golden ratio is the limit of the ratio of consecutive Fibonacci numbers, and describes the golden ratio as a precious jewel. Geometry has 2 great treasures. One is the theorem of Pythagoras, and the other the division of a line into extreme and mean ratio. The first we may compare to a measure of gold. The second we may name a precious jewel. These 2 treasures are combined in the Kepler triangle. Charles Bonnet points out that in the spiral phyllotaxis of plants going clockwise and counterclockwise were frequently 2 successive Fibonacci series. Martin Ohm is believed to be the first to use the term goldene Schnitt to describe this ratio, in 1835. Edouard Lucas gives the numerical sequence now known as the Fibonacci sequence its present name. Mark Barr suggests the Greek letter phi, the initial letter of Greek sculptor Phidias' name, as a symbol for the golden ratio. Roger Penrose discovered in 1974 the Penrose tiling, a pattern that is related to the golden ratio both in the ratio of areas of its 2 rhombic tiles and in their relative frequency within the pattern. This in turn led to new discoveries about quasi-crystals, applications and observations. Aesthetics de Divina Proportiona, a 3-volume work by Luca Pacioli, was published in 1509. Pacioli, a Franciscan friar, was known mostly as a mathematician, but he was also trained and keenly interested in art. The Divina Proportiona explored the mathematics of the golden ratio, though it is often said that Pacioli advocated the golden ratio's application to yield pleasing, harmonious proportions. Livia points out that the interpretation has been traced to an error in 1799, and that Pacioli actually advocated the Vitruvian system of rational proportions. Pacioli also saw Catholic religious significance in the ratio, which led to his work's title. The Divina Proportiona contains illustrations of regular solids by Leonardo da Vinci, Pacioli's longtime friend and collaborator. Architecture. The Parthenon's facade as well as elements of its facade and elsewhere are said by some to be circumscribed by golden rectangles. Other scholars deny that the Greeks had any aesthetic association with golden ratio. For example, Midhat J. Ghazale says, it was not until Euclid, however, that the golden ratio's mathematical properties were studied. In the Elements, the Greek mathematician merely regarded that number as an interesting irrational number. In connection with the middle and extreme ratios, its occurrence in regular pentagons and decagons was duly observed, as well as in the dodecahedron. It is indeed exemplary that the great Euclid, contrary to generations of mystics who followed, would soberly treat that number for what it is, without attaching to it other than its factual properties, and Keith Devlin says, certainly, the oft-repeated assertion that the Parthenon in Athens is based on the golden ratio is not supported by actual measurements. In fact, the entire story about the Greeks and golden ratio seems to be without foundation. The one thing we know for sure is that Euclid, in his famous textbook Elements, written around 300 BC, showed how to calculate its value. Later sources like Vitruvius exclusively discuss proportions that can be expressed in whole numbers, i.e., commensurate as opposed to irrational proportions. A 2004 geometrical analysis of earlier research into the Great Mosque of Cairo reveals a consistent application of the golden ratio throughout the design. According to Busora and Mazuz, They found ratios close to the golden ratio in the overall proportion of the plan and in the dimensioning of the prayer space, the court, and the minaret. The authors note, however, that the areas where ratios close to the golden ratio were found are not part of the original construction, and theorize that these elements were added in a reconstruction. The Swiss architect Le Corbusier, famous for his contributions to the modern international style, centered his design philosophy on systems of harmony and proportion. Le Corbusier's faith in the mathematical order of the universe was closely bound to the golden ratio and the Fibonacci series, which he described as rhythms apparent to the eye and clear in their relations with one another. And these rhythms are at the very root of human activities. They resound in man by an organic inevitability, the same fine inevitability which causes the tracing out of the golden section by children, old men, savages and the learned. Le Corbusier explicitly used the golden ratio in his modular system for the scale of architectural proportion. He saw this system as a continuation of the long tradition of Vitruvius, Leonardo da Vinci's Vitruvian Man, the work of Leon Battista Alberti, and others who used the proportions of the human body to improve the appearance and function of architecture. In addition to the golden ratio, Le Corbusier based the system on human measurements, Fibonacci numbers, and the double unit. He took suggestion of the golden ratio in human proportions to an extreme. He sectioned his model human body's height at the navel with the two sections in golden ratio, then subdivided those sections in golden ratio at the knees and throat. He used these golden ratio proportions in the modular system. Le Corbusier's 1927 Villa Stein in Garches exemplified the modular system's application. The villa's rectangular ground plan, elevation, and inner structure closely approximate golden rectangles. Another Swiss architect, Mario Botta, bases many of his designs on geometric figures. Several private houses he designed in Switzerland are composed of squares and circles, cubes and cylinders. In a house he designed in Oroglio, the golden ratio is the proportion between the central section and the side sections of the house. In a recent book, author Jason Elliott speculated that the golden ratio was used by the designers of the Nakshi Jahan Square and the adjacent Lot Foller Mosque. Painting, the 16th-century philosopher Heinrich Agrippa drew a man over a pentagram inside a circle, implying a relationship to the golden ratio. Leonardo da Vinci's illustrations of polyhedra in De Divina Proportione and his views that some bodily proportions exhibit the golden ratio have led some scholars to speculate that he incorporated the golden ratio in his paintings. But the suggestion that his Mona Lisa, for example, employs golden ratio proportions, is not supported by anything in Leonardo's own writings. Similarly, although the Vitruvian Man is often shown in connection with the golden ratio, the proportions of the figure do not actually match it, and the text only mentions whole number ratios. Salvador Dali, influenced by the works of Matilde Gicker, explicitly used the golden ratio in his masterpiece, The Sacrament of the Last Supper. The dimensions of the canvas are a golden rectangle, a huge dodecahedron, in perspective so that edges appear in golden ratio to one another, is suspended above and behind Jesus and dominates the composition. Mondrian has been said to have used the golden section extensively in his geometrical paintings, though other experts have disputed this claim. A statistical study on 565 works of art of different great painters, performed in 1999, found that these artists had not used the golden ratio in the size of their canvases. The study concluded that the average ratio of the two sides of the paintings studied is 1.34, with averages for individual artists ranging from 1.04 to 1.46. On the other hand, Pablo Tosto listed over 350 works by well-known artists, including more than 100 which have canvases with golden rectangle and root 5 proportions, and others with proportions like root 2, 3, 4, and 6. Book design. According to Jan Tschichold, there was a time when deviations from the truly beautiful page proportions 2 to 3, 1, square root 3, and the golden section were rare. Many books produced between 1550 and 1770 show these proportions exactly, to within half a millimeter. Design. Some sources claim that the golden ratio is commonly used in everyday design, for example in the shapes of postcards, playing cards, posters, widescreen televisions, photographs, light switch plates and cars. Music. Erno Lendvay analyzes Béhécute La Bartók's works as being based on two opposing systems, that of the golden ratio and the acoustic scale, though other music scholars reject that analysis. French composer Éric Satie used the golden ratio in several of his pieces, including Sonneries de la Rose plus Quoi. The golden ratio is also apparent in the organization of the sections in the music of Debussy's Reflets dans l'eau, from Images, in which the sequence of keys is marked out by the intervals 34, 21, 13 and 8, and the main climax sits at the Phi position. The musicologist Roy Howard has observed that the formal boundaries of La Mer correspond exactly to the golden section. Trezisi finds the intrinsic evidence remarkable, but cautions that no written or reported evidence suggests that Debussy consciously sought such proportions. The composer John Painter has pointed out a significant feature in the harmonic structure of the blues. In the 12-bar blues, the main golden section point should be halfway through bar 8. In fact, this is the very point at which we prepare for the really interesting subtleties of harmony in bar 9. Similarly, another important chord change occurs across bars 4 and 5, and that turns out to be GS2. Nature. Adolf Ising, whose main interests were mathematics and philosophy, found the golden ratio expressed in the arrangement of parts such as leaves and branches along the stems of plants and of veins in leaves. He extended his research to the skeletons of animals and the branchings of their veins and nerves, to the proportions of chemical compounds and the geometry of crystals, even to the use of proportion in artistic endeavors. In these patterns in nature he saw the golden ratio operating as a universal law. In connection with his scheme for golden ratio-based human body proportions, Ising wrote in 1854 of a universal law, in which is contained the ground principle of all formative striving for beauty and completeness in the realms of both nature and art, and which permeates, as a paramount spiritual ideal, all structures, forms and proportions, whether cosmic or individual, organic or inorganic, acoustic or optical, which finds its fullest realization, however, in the human form. In 2010, the journal Science reported that the golden ratio is present at the atomic scale in the magnetic resonance of spins in cobalt niobate crystals. Since 1991, several researchers have proposed connections between the golden ratio and human genome DNA optimization. The golden ratio is key to the golden section search. Perceptual studies by psychologists, starting with Fechner, have been devised to test the idea that the golden ratio plays a role in human perception of beauty. While Fechner found a preference for rectangle ratios centered on the golden ratio, later attempts to carefully test such a hypothesis have been, at best, inconclusive.